Topic is binary search trees. So in this video we'll learn about what is binary search tree and the properties of binary search tree. So here is a binary search tree. Let me define it. It is a binary tree in which for every node all the elements in its left subtree are smaller than that node and all the elements in the right subtree are greater than that node. So if you look at this also, elements in the left subtree, there is only one element that is smaller and here the element is greater. For this node, this is smaller and this is greater. So this binary tree is useful for searching. That's why it is named as binary search tree. How it is useful for searching, I'll explain. Suppose I am searching for a key value 40. Then start from root, search for 40. Is this 40? No, 40 is greater than this one. So definitely 40 is on the right hand side. Go to right hand side. Is it 40? No, this is 50. So 40 must be on the left hand side of 50. Go on left hand side. Yes, element is found. So we have compared only few elements in a tree and found the result. So this is useful for searching an element in less number of comparisons. So this is more like a binary search. Binary search is applied on a single array in a list of elements, but this is upon binary tree. So the behavior is similar to binary search. So the search time depends on the height of a tree. We'll learn about search in more detail in other videos. Now let us learn about the properties. First thing, binary search tree will not have duplicates. It will not have duplicates. Now the second one, if we take the in-order traversal of binary search tree, we get the list of elements in sorted order. Let us check. I will perform in-order traversal of this one. Start from root. Move around the boundary. Yes, we have reached the bottom. 10, 15, 20, 30, 40, 50, 60, over. So we got the elements in the sorted order. So in order gives sorted order. In order gives sorted order. Then third property. If we have some nodes, then how many different binary search trees can be created for same set of nodes? So number of binary search trees for n nodes. So the third and the last one is number of binary search trees for n nodes if n nodes are given. So I'll remove this and show you for n nodes how many binary search trees are possible. See here I have 3 nodes 10, 20, 30. Then I want to generate binary search tree from those 3 nodes. So what are the different shapes possible? So we know very well that if we take the in order of a binary search tree, we should get the elements in sorted order, means same order. So always it should be sorted order. So if you remember, for the same pre-order, how many trees are possible? We saw it one of the video. Now for same in order, how many trees are possible? I will draw them, then we will see. Yes, 5 trees are possible. For 3 nodes, 5 different shapes are possible. So I have taken 5 shapes. Now in each shape, the elements are filled such that if you take the in order, so we get 10, 20, 30 for all these trees. If I change the arrangements of these elements, I may not get the same in order. So each shape can be filled only in one way to get the same in order. So you already know the formula. For 3 nodes, when 5 trees are generated, then for n nodes, how many trees can be generated? So 2n Cn by n plus 1 trees can be generated. Catalog number. So if n nodes are given, various shapes binary trees can be generated and that number is 2n Cn by n plus 1. And one more point we observe, again I repeat the point. In one shape, the key elements can be filled only in one way. If I write 20 here, 10 here, I will not get the same in order. Then let us see how we can represent this binary search tree. Binary search tree is represented using linked representation. Linked representation. If you want, you can use array also, but mostly it is done using linked representation. So I will draw a link representation for this one. So this is the link representation of this binary search tree. So that's all. Introduction to binary search tree. We have also learned about its properties. Now next video we will learn how to search in a binary search tree. Now let us look at searching in a binary search tree. I have an example of binary search tree here. I will show you the procedure by taking some keys. Suppose I want to search for a key value, that is 25. Then for searching 25, you can see that 25 is present here. Start from root. Take a temporary pointer on the root of a node. Now let us see the procedure. What are the steps? Wherever t is pointing, check for the data and compare with the key. Key is smaller than the data. So if key is small, move t on left child. The next same thing repeating step. Wherever t is pointing, check the data and compare with the key. Key is greater than data in this node. So move t on right side. Then again repeat. Check wherever t is pointing. Data, compare. Yes, it is same. So element is found in that particular node. So that's how search is very simple. So in how many comparisons I got this element? 1, 2, 3. 3 comparisons I got the element. Now I'll take one more key element. Key is 40. Start from root. Now start the procedure. Compare data with the key. Key is greater than this data. Move t on right side. Then again repeat. Compare key with the data. Key is equal, matching, element found. So in how many comparisons we found? Just in 2 comparisons I found this. So it means if I am searching for 30, I will get it in just 1 comparison. So maximum how many comparisons required for searching? If I am searching for these elements which are in the leaf, then the maximum comparisons are dependent on the height of a tree. Yes, the time taken for searching depends on height of a tree. So I can say that the time is order of h, where we know well that height of a binary tree can be minimum log n and maximum n. So height can be from log n to n. So we can go for minimum one and say it is log n. So minimum time is log n. So the time taken for searching in a binary search tree is log n. Next, we look at unsuccessful search. See, these 2 searches, the key elements were present in the tree. So this is successful search. If the key element is not present, then what happens? Let us take a key element, 21. Start searching. Start from root. Compare data with the key. Key is smaller than data. So go on left side. Compare data with the key. Key is greater than this data. So move on right side. Compare key with the data. Key is smaller than this one. So move on the left side. T became null. On the left side of 25 it was null. So T became null. So we have reached the end of binary search tree. So it means the element is not found. Unsuccessful search. So in unsuccessful search also, maximum how many comparisons are done? 1, 2, 3. This is null, so we did not do anything. So maximum comparisons are equal to the height of a tree. So height, we assume that it is minimum, right? We don't assume that it is maximum. We assume it is minimum, so it is log n. Next, I will write down a recursive procedure for performing search in binary search tree. Function name is rsearch, recursive search, which takes pointer to a node, call it as t, and the key element that we want to search. What it will return, I will write at the end. Every time what we have to do, whether that t is null or not null. If it is not null, then we compare. If it is null, means element is not found, and we will stop. So first I will write down if t is null. I will write down failure condition first. If t is null, then return null, means element is not found. Otherwise what? Compare. If key is equal to t is data, if it is matching, then the key is found. Then return t. So it should return a pointer to a node in which that key is found. Else, if key is less than t's data, if it is on the left hand side, then perform search on the left subtree recursively. So it will call itself recursively r search by passing t's left child and key. This result will be returned. Otherwise, means it's not matching, it's not less, then definitely it is greater. So search in the right subtree, r search in right subtree. So this is a recursive function for searching in a binary search tree. So this is a recursive function for searching in a binary search tree. And if you observe, first it is comparing for the data and the last statement is calling itself. Either this statement or this statement. So if the last statement in a function is a recursive call, then it is called as a tail recursion, right? So it's a tail recursion. Anyway, we have solved enough recursions. You can understand how this is working. I don't have to trace it and show you. So that's it. This takes log n time, that is equal to the height of a tree for searching. Now let us look at iterative function or iterative function, that is using loop. So search function which takes a pointer to a root node and the key that we want to search. Suppose we want to search for a key 25, then t starts from root. So t is at root. So when we call this function, we'll be passing root to this function. Now what it does? Every time check the data with the key. If key is equal to t's data, if key is equal to t's data, means the data is found. So return t, data is matching. If it is not matching, check if it is less. If it is not matching, check if it is less. If it is less, then go to left side. So else, if key is less than t's data, if so, then move t to left hand side. T will move on left hand side. See, our key is smaller, so it has to move on the left hand side. Otherwise, if the key is greater, then it has to move on the right hand side. In every step, it has to do these things. So else, move t upon right side. So I have already checked the condition for equal and less, otherwise it is greater. So this process I have to repeat. So this should come in a loop, while. Let me trace this once again for the key 25. T is pointing here, that is at root. Then first step, key is equal to data. Is it equal to data? No. Is it less? Key is less? Yes. Move t on left side. Then continue. Again check, is it matching with the data? This 20 and 25, they are not same. Is it less? Key is less, 25 is less than 20? No, greater. So move on the right hand side. Then continue once again. Now check, is it matching? Yes, matching. Return, it will stop. So key is found. Suppose this was not a 25, this was 26. Then, is it matching with the data? No. Key, is it less than this one? Key is not less, it's greater. So move on the right side. So right side is null. T is null. Continue. No need to continue. T became null. So it means this repetition we should do as long as T is not null. If T becomes null, then stop. And when you stop, come out of the loop, then say return null. So this return null, it returns null when the key is not found. If the key is found, it will return here. So that's all with the search process. So this is a so that's all. This is the iterative version of search. So that's all. This is the iterative version of search on a binary search tree. So search time already we have analyzed, so it is log n, height of a tree. So that's all. This is a search procedure for searching in a binary search tree, and it is iterative. Now one thing I would like to show you here, that we saw a recursive function. In a recursive function, it was a tail recursion. Now Once we learn that when you convert a recursion into iteration, then you may need stack, right? But here we don't need any stack. This is implemented just using a loop. We don't need any stack. So always it's not required. And when it is a tail recursion, definitely you don't require. If a tail recursion is converted into loop, then you don't need stack. So that's it. Now we'll learn about inserting in a binary search tree. How to insert. Suppose I want to insert a key value 38. So by using this example binary search tree, let us learn how to insert 38. So the first step for insertion is search for key value 38. If this 38 is already present in binary search tree, then we should not insert it. We should not insert it. So first of all, find out whether it is there or not there. So for that, we have to search. So the first step is search. And already we know how to search for a key. Let us repeat the process and search for this 38. So we will start searching from here. So I am taking a pointer T and let us start searching for 38. 38 key, is it equal? No, it's greater than this one. So move T on the right hand side. Okay. Then 40, 38. 38, is it equal? No, 38 is smaller than that one. So move T on the left hand side. 35, 38, is it equal? No, 38 is greater than this one. So move T upon right hand side. So T became null. So T became null, the element is not there. 38 is not there in binary search tree. So we can insert it. So where it should get inserted? See, we were searching for 38 and we have terminated here. So it means this was the place of 38. If suppose 38 is there in the linked list, if suppose 38 is there in a binary search tree, then it must be there. It is greater than 38 and less than 40. So it should be as a right child of 35. So yes, insert it at the same place. Okay, let us insert it. So I should create a new node and link it with right child of 35. That's it. So it can be inserted. But for linking with the right child of 35, I need a pointer on 35. Do I have a pointer on 35? No. T actually became null. Now for inserting 38, I should create a new node and link it as a right child of 35. That's it. It will be inserted. So we need a pointer on 35 also. So for this, we can have a tail pointer. So let us use a tail pointer. So I'll again search for 38 along with the tail pointer. Let us start. T is pointing here and R is also one more pointer, that is null. Is it matching? No, this is greater. So move T on right side, but before that bring R here and move T on right side. Is it matching with 40? No, 38 is less. So bring R upon T and move T to left child. Is it matching with 35 and 38? They are matching? No, 38 is greater, so it should be on right side. So bring R upon this node and move T to the right child. Now T became null. T became null means element is not there. We can insert it. Where? Right child of 35. Who will help now? Pointer R will help. So we need a tailing pointer. Otherwise, we should again search from the root. So the procedure is similar to search. Only thing we need is tailing pointer, and if T became null, create and insert a node. That's all. So I will write down the procedure. So insert function, pointer to root, T is a pointer to root, and the key that we want to insert. So for this we need a tail pointer. So I will declare a pointer R, which will be initially null. I have to just search for the key, right? Search for the key. So for searching, we need a loop, that is T is not equal to null. Then we have to check and move T. But before that, R should come upon T. Then check if key is equal to T's data. If it is matching, means key element is already there. So don't do anything, just return. So even if you have void, you can say return. Return will just stop the function. If match is found, don't have to insert. Else, if key is less than T's data, then move T on left child. else move t upon right child. This process will continue. Either if the key is already found, it will stop. If the key is not found, t will become null and stop, and where r will be upon the node just before t. So using r, we have to link a new node. So first of all, create a new node and insert it there. So when we can do if t has become null and it has came out of the loop. So for creating a node, I need one more pointer. So I'll take a pointer name as p. Then here I will write on the code. So here I have created a new node and also set the data, that is key value, and made left and right child as null. So this all I have done using pointer p. So I'll just remove t here and create a new node with the help of pointer p, enter the key and make this as null. So these are the steps I have done. Then this p should be linked as a left child or right child. So I should check it again, right? As per my example, it comes as a right child, but before linking, I should check it. So if this key is less than t's data, it should come as left child. Otherwise, it should come as right child. So here I will write on the code. If p's data is less than r's data, then r's left child should be p. Otherwise, else r's right child should be p. So check once again and connect it. So this will be connecting to this one as a right child. That's all. So insertion is more like searching only. So the time for inserting is order of log n only. That is height of a binary search tree. For creating entire binary search tree, I should first of all create root. Then rest of the keys I can insert them by using this function. So next let us see, we will take some key values and learn how to create a binary search tree by inserting the keys one by one. Let us look at recursive insert function for binary search tree. We can generate an entire binary search tree by inserting keys one by one. So we can call this function every time for inserting a key. As the function is recursive, so already I have written the function. I will trace the function and show you. Suppose from main function, I have a root pointer which is already null. The first key I will insert, I will call insert function by passing this root and key is 30. See, I am calling insert function for the first time by passing root which is null right now, and I am passing key as 30. So what happens, how this works, let us see. So right now root is null, right? So when I call insert function by passing root, so that root is p here and it is right now null. So root is null. So what is the first statement? If p is null, yes, p is null right now. So create a new node, set the key in data and set left and right child as null and return this t, that new node. So create a new node with the help of temporary pointer. Insert data 30, that is key. Make this left child and right child as null, then return t. So this node's address is returned from there. So that address I can take it in root. So root will be pointing on that node. So this is the first step. So when I am creating first node, root should point on that one. That is the reason I have assigned it with root. So root was null. Now root will be pointing on that one. This is the first step. Now let us insert few more keys. I will say insert. I will pass root now. Root is pointing there on that node. Root and the value is 20. I don't have to assign it to anything now. Already I have root pointing on that root node, that is first node. Let us see. P is upon root. Yes, P is upon root. Then P is null. No. So it will not enter into this block. Then key that I have sent 20. Is it less than P's data? Less than P's data 30? Yes, it is less. So go on which side? Insert upon left child. So it will call itself again. So again the insert function is called by passing P's left child. So what is P's left child now? P's left child is null, right? This left child is null. So this is null. So it will call itself. Right now P is null. So create a new node. Okay, create a new node with the help of T and insert this key set this as null. This is what the common work done every time. When the pointer is null, create a node, set the data and initialize pointers to null. That's what the common steps are. And return this. So this T is return. New node's address is returned. So when it returns, it goes back to the previous call. And in previous call where P was here. First call P was here, right? So in that call, P's left was null. Now you can see that P caps left child or P's left child is assigned with the result returned by this insert function. So it will return the address of this node. So it will be assigned here and it will be pointing here. So from this call also it will return. So it will return the same address P from this node. So it will go back to the previous call. So there was no previous call. This was the first call. So this is the only important statement that I have to explain you. That is, a new node is created and assigned as a left child. So when it returns, it will return the new node's address that will be assigned to the left child. I will insert one more key and show you. Insert 25 and the root is passed. Insert 25, root is passed. So this P becomes root. So P will be pointing on this one. Is the P null? P is not null. It will check key, the value that I am inserting, 25. Is it less than P's data? Less? Yes, less. So call insert again on left child. So a new fresh call will be made upon this left node. So P will be pointing here. Again, P is not null. So again call. P is null? No, it's not null. Then here, key, is it less than P data? 25, is it less than 20? No. Key is greater than P data? 25, is it greater than 20? Yes. So call itself again upon right child. So P will call itself again upon right child. So right child was null. So right now P is null. So in this call, P is null. So a new node will be created, initialized, and its address is returned. A new node is created, initialized with the key that we have given. These are made as null. Its address is returned. So from where it has came? It has came from this node. So P will go back to that node in the previous call. So what was the statement? It's not completed right now. This assignment has to be done. So P's right child will be assigned with that return address. So P's right child will point on this one. So this call has finished. So it went back and assigned this link. Now this call also finishes. So return P. So simply it goes back to the previous call, right? From here it has came to the left side. So it will try to assign the same address again here. And it will go to the previous node. So this address will be, see, like this address is assigned here. So this node's address will also be assigned here. So it's the same address only. It makes no difference. So reassignment of the same address will be done. Then from this call also it finishes. So that's the end because that was the first call. So this is how the keys will be inserted. I can go on writing insert function for inserting various keys in binary search tree. So that's all. This is the recursive function. So I'll show you the demo of this function. I will include it in the program and show you a demo of this function. Let us see how to create a binary search tree from given set of keys. So the procedure is very simple and easy. So let us generate a tree. So here we have to insert all these keys one by one in the same order in which they are given. So let us start. First key is 9. I don't have any node right now. So create the first node and make root point here. So this was the first node. Now next 15. Start from root. 15 is greater than 9. So it should come on the right hand side. Yes, insert it on right side. Then 5. Start from root. 5 is smaller than 9. So it should come on the left hand side. Yes. Then 20. Start from root. 20 is greater than 9. Go to right. 20 is greater than 15. So go to right and insert 20 here. Then 16. 16. Start from root. 16 is greater than 9. Yes. So go to right side. 16 is greater than 15 also. Yes. Go to right. 16 is less than 20, so insert it on the left hand side. Then 8, start from root. 9, that 8 is smaller, so come to this left side. Left side 5, 8 is greater than 5, so insert it as a right child. The next is 12, start from root. 12 is greater than 9. Go to right side. 15, so 12 is less than 15, so insert it as a left child. Then 3, start from root. 3 is less than 9, go to left. It's less than 5, go to left and insert it here. Then 6 is less than 9, go to left. It's greater than 6, go to right. Less than 8, insert it on left. So that's it. This is so simple in generating a binary search tree. What is the time taken for creating a binary search tree? See, we have inserted n elements, right? We have inserted n elements. Then each element we were searching and finding its position and inserting it. Each element. So searching takes how much time? Searching takes log n time. We are assuming that the height of a tree is log n, so search takes log n time. So searching we have done for every element, so n times we have searched. Then creating a node and linking, that will take constant time. Searching takes log n time, so that log n is done for n times, so the time is order of n log n. That's all about creating a binary search tree. In this video, we will write a C language program for binary search tree. In this program, I will show you how to insert an element in a binary search tree, how to perform search, and also we will see how to perform in-order traversal that already we have seen. Same in-order traversal will perform. Let us give the project name as BST, that is binary search tree, and the language is C language. Yeah, project is ready. I'll clear off all the comments. Here, first of all, I should define a structure for binary search tree, structure for a node of a binary search tree. So I will say struct node, and inside this I need three members, that is left child, data, integer type data I am taking, and struct node right child. Then here globally I will declare a root, that is pointer of type node, and I will also initialize it as null. So initially nothing is there in binary search tree. Now let us write a function for insert. Void insert. I will take the key value that has to be inserted. Now already root is globally accessible, so I will directly access this root here. Inside this insert function, I may require some temporary variable. So the first variable that I will take, that is node t, that will point upon root. Then also I will take a node pointer, that is r, that will be following t, and also I will create one more pointer, that is p, that is used for creating a new node. Using this p, I will create a new node. Now in this function, first of all, I will check whether root is null. If root is null, then this is the first node. So simply I have to create a new node and make it as a root node. So by using pointer p, I will create a new node. For creating a new node, call malloc function. So for that, first of all, typecast node star, then malloc function, and here size of struct node. Then p's data, I will set it as key value that I want to insert, and p's left child as well as p's right child, I will assign them as null. So this has to be done when root is null, means this is the very first node. Otherwise, we will run the procedure what we have seen on whiteboard. So on whiteboard, we have seen that while t is not equal to null, we will continue searching for a key value, and r will be following t. And here we write on the procedure same as searching, that if key is less than t's data, then move t upon left child, else if key is greater than t's data, then move t upon right child, else key element is found. So if key element is found, we are not going to insert anything, simply we will return, means we will stop the procedure. Now once we have came out of the while loop, so t will become null and r will be pointing on some location where we have to insert a new node. So for that, first of all, I will create a new node. So p assign new node. So already we have written this code for creating a new node. I will copy that portion and paste it here. So it's the same code for creating a new node. Now once the new node is created, now I should link it with a binary search tree. So I have to again check using r if key is less than r's data, means the new node should come on the left hand side. So directly I will write on here r's l child should be assigned with the p, that is new node, else r's right child should be assigned with that new node p. That's it. This is how a new node will be inserted in a binary search tree. So the code is a little lengthy. This is the portion which we have already seen on whiteboard. So I have added extra code here that if this is the first node, that is root is already null, then we'll do this. Then after creating the first node, I should stop the procedure. So I can say return. So here I don't have to write else, because once it has inserted a first node, very first node, then it will stop. Otherwise, if it is not null, then it will enter here. Then it will enter here and insert a new node at a given position. This is perfect. Now next, I will write on a function for performing in-order traversal so that I can confirm the creation of a binary search tree. The in-order traversal of a binary search tree gives sorted order of elements. So let us try this in-order function. I will write on a recursive function. So it will take struct node pointer. Let us call it as p, that is for root node, and here if p means p is not equal to null. Already you know the procedure for in-order traversal, just I am writing it here. Go on p's left child, then printf, print the data, %d, then p's data, then in order p's r child. That's all. I have the functions ready, that is inserting an element and performing in order so that I can see the values that are inserted in binary search tree. Now let us write on the main function and test these insert and in order function. Then later on I will write on search function. From main function I will perform insert operations. I will insert a key 10. This should be a root. Then insert 5. This should go on the left hand side. Then insert 20. It should be on the right hand side. Then insert 8. So it should be on the right hand side of 5. Then insert 30. It should be on the right hand side of 20. Then I will perform in order by passing root of a tree. So when I perform in order, I should get the elements in the sorted order, because in order traversal gives sorted order. Then here also I will give a new line so that I can get a gap. Now let us run this one. If there are any errors, we will remove those errors. Nothing is displayed. So there may be some error in this one. It's not a syntax error, but maybe a logical error. Let us see where I have missed it. So it means it's not displaying in order, means these elements are not inserted properly. So where it could be, even a first value is not displayed. So it means the problem is with the root. So let us check with root. Root is null, yes. Then when I am creating first node, when root is equal to null, I am inserting a new node with a pointer p. Oh, I missed one thing here. Root should be pointing on this new node p. So even the first node was not created means the problem was with the root. So here, yes, I missed this one. When root is null and I am creating a new node, then root should point on that new node. Now let us run the program once again. Yes, I got the elements in the sorted order 5, 8, 10, 20 and 30. Perfect. Now one thing I would like to show you, before performing in-order traversal, I'll just put a breakpoint here and run the program. Now here you can see in the debug area, root is there. Root is having data as a 10 and the left child and the right child. So if I expand left child is having data 5. And if I expand its left child, then it is having data nothing on the left hand side. Then if I expand the right child of 5, then you can find 8 here. Then let us go on the right child of this root. I'll close this one. This is the right child of root. Right child is 20 and its right child is 30. And 20's left child is null. Nothing is there. So you can see the complete structure that is prepared in the heap. So the tree that I wanted to create can be seen here. So that's it. We have finished with this insert and in-order traversal. I'll remove the breakpoint. Now I will write down a function for search. So the search function we have seen, I will write on that function. So the logic for search is same as what we have used already in insert function, but I will write on. Search function should return a node in which the key value is found. So this is struct node search for key. Now for searching, I need a pointer that should start from root. So I will take a pointer t that will start from root, and this will be searching for the key. Now the procedure is simple. While t is not equal to null, check if key value is equal to t's data. If it is equal to t data, then return t itself. Else check if key value is less than t's data. Then take t upon left child, t assign t's l child. Else move t upon right child, t assign t's r child. That's it. And if we come out of the loop without any key found, then simply return null. So that's it. This is the search function already we have seen, and this is a iterative version. Now here inside the main function, already I have inserted few elements, then also I am performing in-order traversal. Then after this, I will perform search, and search returns a node structure, right? It will return the structure of a node in which the value is found. So I will take a pointer, that is structure pointer, on the top inside the main function. I'll declare it struct node. I'll take a temporary pointer for taking the result from search. Then this temp assign call function search, and I want to search for a key that is 20. After this, I will check if it is returning anything. If it is not equal to null means the element is found. So simply I will print a message that element %d is found. And from that node, I'll take the data, that is temp's data. The value that is the node that is returned, from there I will print the data. Otherwise, I can print a message that element is not found. Element is not found. /n. That's it. I'm searching for a key value 20. Just remember this. I'll run the program and show you. I should get the result that is element is found, and it should print its data. Yes, element 20 is found. Yes. Then I'll give the number as 2. Let us run and see. 2 is not there in our binary search tree. Element is not found. Yes, here you can see the message. Element is not found. I mistyped here. So it's a typing mistake. Element is not found. So that's all. The search function and insert function, both the function we have seen. And already I have shown you recursive version of search and recursive version of insert. So you have to do it as student exercise. That's all in this video. Now we look at deleting from binary search tree. So here is an example binary search tree. Let's see how to delete any key. So I'll take various examples and show you. So first key I want to delete is 25. So what's the procedure? So the procedure is search for the key. If found, then delete it. That's simple. Search for 25. Start from here. 25 is smaller. Go here. 25 is greater than this. Go to right. Yes, found. Then delete this node. If you delete this node, any node, then you have to make its parent link as null, right? If it is linked representation, we have to make this as null. Yes, we can make it as null and this node is deleted. So this was simple. I'll put back the node as it is. Now let me take another example. I want to delete a key 43. Search for 43. 43 is greater than this and greater than this one. Less than this, come to left. It's greater than this. Yes, found. So delete the node. Then make this right child link as null. That's it. So node is deleted. So I'll put it back. So these were simple examples. Next, I want to delete a key 42. Search for 42. 42 is greater, and this is smaller than this one. Yes, found. Now the problem is there. What is that? If I delete 42, then I have to modify the link of parent. But 42 is also having a child. Then, okay, it is having just one child, no problem. Its child will take its position. So if 42 goes away from here, then this will be pointing onto its child. That is becomes a left child of 45. So we saw one more thing now, that if the node is getting deleted and if it is having one child, then that child will take its place. So again back to the same tree. So the procedure we have learned so far is, if you want to delete, search for the key. If found, then delete the key. If it is not having any children, no problem. If it is having one child, then let that child take its place. Now what if I want to delete key 30? I want to delete this. Then after deletion, who will take its place? You may be saying 20. Then who will take the place of 20? 25 or 10? Anyone? Or else I say that no, 40 will take its place. Then who will take the place of 40? 45. Who will take the place of 45? So many changes we have to make. Instead of doing this way, the other way is, for 30, find out in order predecessor. Means if you perform in order, which node comes before 30? So 25 comes before 30. This is in order predecessor. And who is in order successor of 30? Who comes after 30 in order traversal of this tree? This one. So this is in order successor. So there is in order predecessor, there is in order successor. So for a node, this is in order predecessor, this is in order successor. If you are deleting 30, 30 is going out, then either in order predecessor will take its place or in order successor will take its place. So in order predecessor may be a leaf and in order successor we assume it is a leaf. Yes, they are leaf. So leaf node will come into its place. So we don't have to disturb so many nodes. So the result of this tree can be 25 as a root and 20 and 10 on this side, 40, 35, 45, 42 and 43. It can be like this. So where 25 is in the root, or it can be 35 in the root, 35 is in the root. Either 25 is in the root or 35 in the root. See here, from here the node is deleted and here, from here the node is deleted. So this is the actual method. When you are deleting any node, then who should take its place? In order predecessor or in order successor? should take its place, right? So how to find in-order predecessor or successor? For in-order predecessor, for deleting a node, go to its left subtree, left, then right. So the rightmost child of a left subtree. In-order successor is leftmost child of right subtree. So you can easily find in-order predecessor, in-order successor. You don't have to perform in-order traversal. You can go to left subtree, then right until you find the last node. Or else go to right subtree, then left until you get the last node. Then, so that's how you can find in-order predecessor or successor. Now one more question remains. Shall I take in-order predecessor or shall I take in-order successor? You can take anyone. You can take anyone. It's your choice. Suppose you want to say that no, right hand side is having more elements, so from there I will bring. Okay, so you can count the number of nodes here and you can count the nodes here. Whichever side is having more number of nodes, from there you can get it. Or else you say no, the height of this right subtree, this portion is larger than this one, then if you want to take this, so find out height and select that one. So otherwise randomly you can select anyone. So we have seen various examples, and when we took 30, then we understood that we have to replace it with in-order predecessor or in-order successor. Then what about 25? When I deleted 25, there was no predecessor successor, right? So directly I deleted the node. Then what happened when I was deleting 43? There was no predecessor successor, so directly I deleted it. What happened when 42 was deleted? When 42 was deleted, there was only one child, only successor, so it has taken its place. So actually I was following same method, right? Always we should follow same method. Now I'll remove this and I'll show you one more example. Suppose I want to delete 40. Then after deleting 40, who will take its place? In-order predecessor. Who is in-order predecessor? This one. See the nodes below 40 only. Then who is in-order successor? This one. This is in-order predecessor, in-order successor. Suppose after deleting 40, I want to bring successor here. 42 will come here. This 42 will come here. But 42 is still having some child. It is not a leaf node. It's not a leaf node. Then I should fill up this position also with its in-order predecessor or successor. So there is only one node that will come in its place. So listen carefully. We were taking in-order predecessor or successor because we wanted to avoid multiple modifications in the tree. But this is the example where though we are taking in-order successor, we have to make multiple modifications. This is gone, 42 has taken its place, then 43 has to come here, right? So if the in-order predecessor or successor is not a leaf node, then you may have to make multiple modifications, right? So quickly I will show you one more example. Suppose this is a binary search tree. I want to delete 10. Then there is no predecessor. Successor is there. Who is in-order successor? 20. So 20 should go there in place of 10. Then this will be vacant. See, this is not a leaf node. Then who will take its place? 30 is an in-order successor of this one. So 30 should come in its place. Again, this is vacant. This is not a leaf node. Again, it's having a child. So 70 should come here. So in this example, we have to make more than one modifications if you are deleting some node in a tree. Now, analysis. What is the time taken for deletion? It depends on the height of a tree. We are searching and modifying it. So it depends on the height of a tree. We say height is log n, right? We are assuming that it is log n. Then after deleting a node, how many modifications required? If predecessor successor is a leaf node, then just one modification. Otherwise, there may be more than one modifications. How many at most? That depends on the height again. So that depends on the height. In this example, you can see that depends on the height. So number of modifications are also log n. Time is log n and the number of modifications may be maximum log n. So that's all. Let us summarize all the things. Then once again, I will show you what all we have done. Let us look at these cases. See, if you are deleting 10, so there is nothing below 10. This is a leaf node. Simply delete 10. Second one, if you are deleting 40, then 40 is having one child. So let that child take its place. and delete 40. Then third, if you are deleting 30 and there are both left subtree as well as right subtree, right? Then let in order predecessor go there or in order successor go to its place. Now, fourth one, if you are deleting a node and if you want in order successor, then this will go in its place. Again, if it is having children, then its in order predecessor or successor will come to its place. More than one modification is required. So actually, there is only one method, this one. When you delete, bring in order predecessor or successor, anyone. If not there, then these are other two cases. And if it is also having its children, then modify that also. That's all about deletion. We will look at a program how to delete. In this video, I will write a recursive function for inserting in a binary search tree as well as a recursive function for deleting from a binary search tree. Already we have written a program for creating a binary search tree, and the insert function was a repeating function, that is iterative function. Already we have seen it. In the same program, I will add a function for recursive insert. Let us write a function. It returns structure node pointer, and the function name I will call it as rinsert because already I have used a name insert for iterative insert function. So it should take a pointer to a root node. So let us call this as a P, and that is a root node, and the key that we want to insert. Now this recursive insert works just like a recursive search function which we have already discussed on whiteboard. So the same method I will follow. Let us start writing the code. If any variables are required, I will declare them afterwards. First thing, if the key is less than P's data, that is root's data. If it is less than root's data, then we should try to insert on the left hand side. So call rinsert upon left hand side of P, that is L child, and the key is the parameter. These are the two parameters. Now this function is going to return the address of a node that I will take it in left child of P. Then else, if key is greater than P's data, that is root's data or the key's data, then I should call upon recursive function should be called upon right child, and its address should be taken in R child. Else means the key is equal, so it's already present there. So we don't have to do anything, simply return P. And even after insertion, I have to return P only. So I'll just write P in every case. So it means else if they are equal, I don't have to do anything. Then when to insert this one? See, while searching, when we reach at a null, when P becomes null, that time we should insert a new node. So in the beginning, I will write on the code now. If a P has become null, means we have reached the last, that is leaf node. Then create a new node. So I'll take a temporary pointer T, and with that I will create a new node, struct node pointer, and I should call malloc function for creating a new node. Size of struct node. So node is created. Inside this node data, I should set the value, that is key, and also I should set its left child as well as right child as null, T's left child and T's R child as null, and return T, so that T is set to the parent node as a left child or right child. It depends on how we were searching. That's it. So for this I need a pointer, that is struct node pointer T. This T I can keep it initialized to null. That's all. This is a recursive procedure for inserting in a binary search tree. Now let us go to the main function and let us use that rinsert function. See, when I call rinsert function for the first time, when I am creating first node, then I should assign this to root. So this should be root assign rinsert. First time I am inserting 10. Then rinsert, and also I should pass this root as parameter in every call. Then R insert, I should pass root as a parameter, root. Because it's recursive, it should take the parameter, the pointer of root itself. And all these functions are R insert. I will modify them. So only the first one I have to take it in root, because when I'm creating first node, when it returns the pointer, that should be taken in root. That's all. Remaining, already I have a function for checking in order traversal, so it will print in order traversal, and also checking a key element whether 2 is present or not. So this time we will check for 20 whether it's present or not. Let us run this program. Yes, it's working perfectly. A binary search tree is created. 5, 8, 10, 20, 30 is the in order traversal, and 20 key is also found. Let us debug this and see how this tree is created. First is root is 10, then its left child will be 5, then right child of 10 will be 20, and then 8 will be on the right hand side of 5, and 30 will be on the right hand side of 5. So actually the structure that we should get is, so here I will draw and show you, just rough sketch I am doing it here. 10 should be in the root, and 5 should be on its left hand side. This should be 5. 20 on the right hand side of 10. This should be 20. A tree should be created like this. And 8 should be on the right hand side of 5. This is 8. And 30 should be on the right hand side of 20. So the keys should be inserted like this. This should be 30. Let us debug our program and check whether the tree is constructed like this or not. I'll put a breakpoint on in order traversal. Before performing in order traversal, all the nodes will be inserted. So let us see how the structure looks like. Let us look at the debug area. Root is there. Root is having value 10. Yes, perfect. Its left child is 5. Yes. And 5's left child is null here. It is null here. And 5's right child is 8. Yes, it is 8. And its left child and right child are 0. Yes, that are nulls. Then let us close this. Then 10's right child is 20. Yes. And its left child is null. Here we can see that it is null. And the 10's right child is 30. Yes, perfect. So that's it. It is perfectly inserting and creating a binary search tree. I'll stop this one. Now let us write a delete function. Delete function will be a recursive function, just like a recursive search or the recursive insert we saw. So let us start writing it. Struct node. It will return a pointer to a node. Delete function. So it should take a parameter as struct node pointer. Let us call it as p. This is going to be a root, an integer key that we want to delete. Then inside this function, I will write on the similar code that first, if key is less than p's data, then we will perform search upon left hand side. So p's l child is assigned with delete function, which will call itself again on p's l child. Then else, if key is greater than p's data, then it is on the right hand side. So we should search an key element on the right hand side. So that will continue on the right hand side by assigning it to r child of p, called delete function, by passing p's r child, as well as key also it's taking. And here in the previous one also I should write key. Yes, now it's okay. Now else means both are equal, means key is found, and this time we have to delete a key. So for deleting a key, already I have shown you how a element is deleted from binary search tree. We can delete an element by replacing it with pre-order. We can delete an element and replace it with the in-order predecessor or in-order successor. So we have two options here. So here I would like to decide which one I should take. I will not blindly follow predecessor or blindly follow successor, but I will decide based on the height of left subtree and the height of right subtree. If the height of left subtree is more, then we will delete an element from the left hand side. Otherwise, we will delete an element from right hand side. If they are equal, we can delete from any side. So let us check the height, and based on the height, we will decide whether to delete from left hand side or right hand side. So first of all, I will find height of P's left child. If this is greater than height of P's R child. Yeah, I have to write on this function height. I'll write it afterwards. So if P's left child is greater, so if P's left child height is greater than right hand side, then we should delete an element from left hand side. So for deleting an element from left hand side, actually we need a in order predecessor. So for that, I will write a function which will find out in order predecessor. So that function I will write down directly here. I will call that function in pre of left subtree. So that is P's L child. So how to find the in order predecessor? It should be a rightmost child of left subtree. Yes, we will get that one. And this I will take in a temporary pointer, let us say Q. Then after finding that element, I should copy the data of a Q. I should copy the data of that in order predecessor in the P's data. So P's data should be changed to Q's data. It should be replaced. Then after replacing, I should delete that node Q. So P's L child should be assigned with, again called delete recursively upon P's L child by a new key. We have to delete this key, that is Q's data we have to delete. Yes, this will recursively call itself. Means we have already seen that while deleting, we may have to modify more than one keys or more than one nodes. So how this works, I will show you. For this, I will draw a diagram and show you. So here is an example binary search tree. Suppose I want to delete 50, then it is not having any right child, so I should get an element from left subtree, that is in order predecessor. So in order predecessor for 50 is 40. So this value should be copied here. Then this node should be deleted. But again, this node is having its left subtree, so its in order predecessor is 30. So 30 should be copied here, and we should delete the node 30. So this is how it is calling recursively itself. Then finally we delete node 30 because it's a leaf node. So physically this node will be deleted, and value 30 is copied here and value 40 is copied here. In this way 50 is deleted. So the physical node deleted is this one, the last one, the leaf one. So that's how we are calling it recursively. So back on this one, if the height of left child was more, then we have perform on the left hand side. Otherwise, we will perform the same thing on the right hand side. So I will take it in else and I will paste it directly the same code. So this time I have to find in order successor upon right child, and this right child, and this also should be a right child. That's it. So recursively perform deletion on the left side or the right hand side depending on the height. Now finally, when I should delete a node, so here I should delete a node, here I should delete a node. If P has became null, means it has become null, actually nothing we have to delete, so simply return null. And second thing, if P is a leaf node, so P is a leaf node means P's left child is not there, is equal to null, as well as P's right child is equal to null. If both are null, means it's a leaf node, and when it is a leaf node, directly we have to delete this node. So here I will write on the code for freeing that node. Free P. P should be freed. And before freeing P, let us check if P is a root node. If P is equal to root node, P is equal to root, then root should be made as null. So we should delete that node. Yes. Then after that we should return null because the node is deleted. That's all. This is the code for deleting. See, this portion is like search process only, and when the key is found, so we have to replace the element by finding in order predecessor or successor. So I have taken an option depending on the height, and when we have reached the leaf node, we should delete that node. And we should also make sure that if this was the last node, that p is equal to root only, then root should be made as null. Then here the required variable I will declare, that is struct node. I have taken a pointer that is q, so I will declare it. Then above this, I should have functions for finding height and in order predecessor, in order successor. So the function for finding height, it should take struct node pointer p, and if p is equals to null, then return 0. Otherwise, I should find out x value and y value. X is height, p is L child, y is height, p is R child. Then return whichever is greater. So already we have seen this code, so I don't have to explain, just I am typing it. Return x plus 1 or else return y plus 1. This is for the code. This is for the height. Then in order predecessor, it should return a node structure, that is in order predecessor, and it should take the parameter also as node structure. Let us take it as p. Now from the point that is node p, we should find out in order predecessor. So it's a rightmost child. So while p as well as, means p should not be null, while p's R child is not equal to null, means it will be going on moving on the right hand side. So rightmost child we will take of left subtree. And finally, it should return p. Now the same way, I will copy this and I will write down the code for in order successor. So I will just modify this. I'll just give some line gaps so that you can clearly see the code that I am typing. This is for in order successor. In order successor. So it should be going on the left hand side now, that is leftmost child of right subtree. That's all. I finished all the function. I have just typed all of them without checking any errors. Now if I compile, if there are any errors, I'll remove them. There is an error. Yes. End of the function. Yes. Inside this recursive delete, at the end, I should return p. Return p as same as what I was doing in insert function. Let us run this. It should run error free. Then we will use delete function. Yes, it's working perfectly. Now let us call delete function. So from these nodes, I will delete one element. So before performing in order traversal, let us call delete function. I will call function name as delete, and we should pass root, and the key that I want to delete is 20. So 20 should be deleted from binary search tree. Let us run this. Yes, 5, 8, 10 and 30. It's working. Let us delete root itself, 10. 5, 8, 20, 30. Let us create this extreme case, that is 50, 10, 40, 20 and 30. If I insert them in this order, I'll get this structure. Then we will delete 50. So root is 50, then its left child is 10, then right child is 40, then left child is 20 and right child is 30. And we will delete 50. Let us check whether it will delete 50 or not. Yes, deleted. If I delete any other element like 30, I want to delete. Yes, 30 is deleted. You can check your results here, right? So 30 is deleted. So it's working perfect. So that's all. These programs are little lengthy and you have to work carefully. And whenever you require, you can do some paperwork also to check how your results are working. And debugging the program is more important if you are getting any errors. And always you have the solution available as PDF below the program, so you can download that PDF and you can compare your program with the PDF. That's all in this video. The topic is generating binary search tree from traversals. Similar topic we have studied in binary trees, just binary trees, but these are binary search trees. And in binary trees we studied that for generating a binary tree we need any two traversals, and among that one of the traversal must be in order. Pre-order plus in order or post-order plus in order. Any one of these combination must be given, then only we can generate a binary tree. Now coming back to binary search tree. For generating a binary search tree, if we are having pre-order and an in order or post-order and in order, then we can generate binary search tree also by following that same old procedure. But in the example, I have only pre-order. What about in order? So I don't have to worry. In order traversal of binary search tree gives a sorted order. This is the property of binary search tree. So I can take the sorted order of these elements like 10, 15, 20, 25, 30, 40, 45 and 50. If I take the sorted order, then I will be having pre-order and in order, then I can follow that old procedure. Yes. So how many traversals should be given to us? Only one traversal is sufficient. That is either pre-order or post-order. In order I can find out. But without in order also, binary search tree can be generated just using pre-order or just using post-order. So we don't need in order. Without that also binary search tree can be generated. So just using pre-order we can generate binary search tree. Let us see how we can generate a binary search tree just using pre-order traversal. Let us create a binary search tree. For this procedure, I need a stack. So I'll take a stack. Let us start. Scan through this pre-order by taking one element at a time. So right now we are at first element, that is pre of 0. So for the very first key, create a node. Create it and make root point on it, and also take some temporary pointer p pointing on it. This is the first node. This is the very first node. So for initial part we have to do it separately, right? Because root should point on that one. So this is the first step. Initial step, not a repeating step. Initial step. Now repeating step starts. First node is created, so binary search tree is ready just with one key. Now move to next. This element, is it smaller than 30? Yes, smaller than 30. So create a new node with some temporary pointer and set that value, make this as null. Make p's left point on this one because this is smaller. And push the address of 30 into the stack, address of 30 into the stack, and move p on this node. So now p is pointing on new node. The next, this is repeating steps, right? Remember, this is repeating step. So one step over. It was small, so we inserted on left side. Otherwise, what we should do, we will see. Next, move to next element. Is it smaller than 20? Yes. So create a new node with the help of temporary pointer and insert the value, make this as null, make this point on this one, push the address of that 20 into the stack and move p on new node. So this I have done it using t. Second, one more step, we have repeated the same thing. Now move to next one. This is 15. Is it smaller than this one? Is it smaller than this one? 10? It's not smaller than 10. Definitely, it is greater than 10. Yes, it is greater than 10. So it's greater than 10 means, shall I insert here or confirm whether it comes there only or not? I have to confirm. How? That element, that next element should be in between these two. It should be smaller than this one and greater than 10. So it should be in between 10 and 20, right? So it is not less than this one, yes. Else it should be greater than this one and less than 20. So where is 20? So the topmost element into the stack, don't delete it, don't delete it. Just check the data from there, 20. So it's greater than 10 and smaller than 20. Yes, 15 is greater than 10 and smaller than 20. Then create a new node with the help of temporary pointer right? And insert that value 15, make this as null, make P's right child belong to this one, and bring P upon this new node. Don't push the address. So this is the difference. When left child, we were pushing the address and going on new node. But when it is right child, just go on new node, don't push the address of 10. We don't have to go back to 10 now. 10's left child, it was not there. Right child, we insert it. So 10's role is over. That node's role is completed. So we don't need it in the stack. Next, move to the next step is repeating. 25, is it less than 15? No, it's not less than 15. Is it greater than 15? Yes, obviously it is greater than 15. Shall I insert at right side? No. You have to check whether it is lying in between the range of this 15 and this node. So what is this node? The address is here. Just take the data. 15 and 20. Is it lying in between 15 and 20? No, that is 25. So it's not in between also. So it will not come as a right child of 15. So if it is within range, insert it. Otherwise, what to do? Pop out this address from the stack and move P here. So upon 20, we got the address of 20. So in this step, we did not move I to the next element because it is not yet inserted. Step is completed. Don't move I. Let us start again. 25. Is it less than 20? No. Definitely it's greater. So if it is greater, it should lie in between this 20 and the topmost element in the stack. Topmost node in the stack is having 30. So it should be between 20 and 30. Yes, it is in between. So if it is in between, insert 25 on the right hand side. New node, link it, move P to new node. Don't push that in the stack. When we are creating right child, we are not inserting the address. Then also move to next element because 25 is inserted. Step completed. Repeat. 40. Is it less than 25? Current node is this one. No. Greater than 25? Yes. But is it lying in between 25 and this value 30? No. 40 is not lying in between these two. Then pop out this address and move P to that address. Don't move I. Let it be there only. Step is completed. Continue. 40. Is it less than 30? No. Is it greater than 30? 40? Yes. Compare the value from here to stack. When stack is not having anything means let it be infinity. Maximum value. Let it be infinity. So it's lying in between 30 and infinity. Yes. So add it as a right child. Create a new node with a temporary pointer t. 40 is inserted. Make this as null. And the P is right child pointing here. Bring P on this one. Now I have shown you all cases. Now remaining two I will finish quickly. Now I is on 50. 50 is it smaller? No. 50 is it greater? Yes, greater. But is it lying in between 40 and nothing is there? So it is infinity. So it's lying in between 40 and infinity. So insert 50 on this side with a temporary pointer and link it. Bring P upon that new node. And also move I. So that 50 is inserted. Now next element is 45. 45, is it less than 50? Yes, it is less than 50. So insert here 45 and link it and push the address of 50 in the stack. Address of 50 is pushed into the stack. Bring P here. Move I. I has reached the end of the pre-order. So the procedure ends and we got the result. So we have reached the end of an array and we got the result. So that's all. This is the procedure. I will write on a function and show you. Yeah, let us write a function for generating a binary search tree from pre-order traversal. I am calling the function name as create from pre-order. It takes the parameter array of integers, that is pre is an array, and also I need the size. In this procedure, I need a stack of pointers. So I take a stack. Then I need a temporary pointer also. So I will create a temporary pointer. I also need I, which will scan through this array. So initially I unassigned with 0. Okay, required things are ready. If anything more, I will declare it. Now start the procedure. The first thing was we created a root node. Assume that root is global. So First of all, create a new node using root directly. Yeah, here I have created root. This is the first root node. And I am using new operator here. We can use malloc function also, right? So sometime I am writing new or malloc, whatever it is. Then set the data from array, pre, and move I to the next element also. Then set left child and right child both together as null. This also null, that also null. That was the first thing we have done. Then make P point on root. P is pointing on root. So this is what we have done. Now the procedure was repeating. How long? Until it reaches the end. So total how many elements are there? 8 elements are there. So n is 8, right? So I should stop when I becomes 8, right? So I should continue until I is equal to 7. So I will write on a while loop because this repetition, these steps are repeating depending on the number of elements in this array. So while I is less than n. When I is equal to n, that is 8, stop. See, I am not using for loop because I is not incremented always. Let us recall what are the steps. First thing, if the element in the pre-order is less than P data, P is pointing here. If it is smaller, yes, if it is smaller, then create a new node with the help of temporary pointer, T assign a new node, set the data. See, if the element from pre-order is less than data, like if you remember for 20, we did that. If it is smaller, then create a new node and set the data, make two children as null, both left and right as null, and make P's left child point here, P's left child point here. Then push that address of P, that is 30, into the stack. Then P assign T, bring P upon T. These were the steps we were doing when the data was small. Otherwise, there is no space here, so I will continue here. I will remove few things and show you. If it is not less, element is not less than P's data, if it is greater, there are two cases. If it is greater, then it should be within range, right? If it is within range, then we create a node and link it. If it is not within range, then we pop out an address from the stack and move P upon that previous node. So those steps I have to write down. So here I have written the steps like element in the pre-order is greater than P's data. And also element in pre-order is smaller than stack top's data. Stack top will return the address and its data, that node's data. And one more thing, I have to write something here such that if the stack is empty, it should be infinity. So I did not write that piece of code. When showing demo, I will write on that. Next, a new node is created, data is set, and the pointers are set as null. P's right child is made as T. That is, P's right will be pointing on T, this one, right? And move P on new node T. Bring P upon this new node T. Otherwise, if this condition fails, then pop out an address from the stack and move P upon that node. Don't do anything. If this condition fails, just move P to the previous node, and I is not moving. It remains on the same element in an array. So that's all. This is the end of if, and this is the end of while loop, and this is the end of function. This loop will create a binary search tree from just pre-order. We don't need in order. Now, little bit of analysis. How much time it has taken? What work we have done? We have just scanned through all these elements. So how many elements are there? N. So time is order of n. From the work that I have done, based on that I told you the time. Look at the code. Code is having loop. Which loop? While loop. How many times it will repeat? I is less than n, and somewhere here and here I plus plus is done. So I is moving until n. So this loop is similar to for loop only. So n times. So this loop I is starting from 0 and up to n it is going. So it is n times. So loop will repeat for n times, and all the statements are simple statements only. All of them takes constant time. So if I count the steps also, 1, 2, 3, 4, 5, 6, 7. Otherwise this may happen. So 1, 2, 3, 4, 4. So maximum 7. So I should say 7n. 7n. 7 steps are there, 7 times n. So this is nothing but order of n. Degree of a polynomial is n, so order of n. That's all. So finally, a binary search tree can be created just using pre-order or just using post-order. So we don't need in order, and it can be generated only in order of n time. Pre-order I have shown you, post-order is your exercise. One hint for the post-order, you have to start from right side. That's all. Let us see what is the drawback of binary search tree. I have set of keys here. Using these keys, I have to create a binary search tree. And I have one more set of keys. For this also, I have to create a binary search tree. If you observe keys 40, 20, 30, 60, 50, 10, 70. So 10, 20, 30, 40, 50, 60, 70. So keys are same, but the order is different. So first of all, I will create a tree for this one also, that one also. Then we'll see what is the drawback. Let us start. First element 40, create a node. 20 is smaller, it comes on left side. 30 is smaller than 40 and greater than 20, so it comes on right side. Then 60 is greater than 40, it goes on right side. 50 is greater than 40 but less than 60, it comes on left side. Then 10 is smaller than 40 and smaller than 20, so it comes on left side. Then 70 is greater than 40, greater than 60, so it comes on right side. So I got this tree. So this is the root of a tree. And what is the height of a tree? 0, 1, 2. So the height is 2. Next, let us generate a tree for those keys. Let us start. First key is 10. Okay, this is root. Then 20 is greater than this one. So insert on the right hand side. 30 is greater than 10 and greater than 20. So it's on the right hand side. 40 is greater. So it is on the right side. 50 is greater. So on the right side. 60 is greater than all these. So it comes here. And 70 is greater than all these. So it comes on this side. So what is the height? 0, 1, 2, 3, 4, 5, 6. So height is 6. For same set of keys, I got this tree of height 2. I got this tree of height 6. So for 7 nodes, these are 7 nodes. So height is 2 means height is log n plus 1 base 2 minus 1. So this is log n. And for n nodes, height here is n minus 1. So it's order of n. So height of this binary search tree is logarithmic. Height of that binary search tree is linear, n, log n. Now let us talk about drawback. The height of a binary search tree can be as minimum as log n, as maximum as n. It depends how you are inserting the keys. It depends on that. So there is no control over the height of a binary search tree. It all depends on order of insertion. Can you control order of insertion? No. Why? See, I am writing a program for binary search tree, and that application, that program, you are going to use it. You are a user, right? Now, how I can control you to give the values properly so that a minimum height is formed? You are using my application, you will be giving the keys as you have or as you are getting, then my program will be generating the tree. So, if you have given the values like this, then it will be like this one. So, I created a situation to make you understand that we cannot control the order of insertion. So, we cannot control the height of a binary search tree. So we need some method to control the height of a binary search tree. So binary search tree itself should control its height. So that's what we call them as AVL trees. So AVL trees are height balanced binary search trees. So how they control their height, we will learn about AVL trees in the next topic. So conclusion here is that height of a binary search tree is not log n always, right? It's not always log n. But we were assuming that it is log n every time. Whenever I was analyzing, I was saying height is log. We are expecting this. So we are using binary search trees expecting that their height will be minimum. But the reality is that it may not be always minimum. It can be linear also. So that's all about drawback of binary search tree.